Welcome back. So now we are going to look into the matrix. Why do we need matrix? We need to tell if whatever you built, the system you built, is good or not good. You need to evaluate it and improve it if necessary. So what we have seen so far is, I keep repeating, but this is how it remains in your mind. We had an input set of documents. We started with Boolean queries and or not, and so that we can output a subset of documents. We saw that for this, we needed to simplify things by looking at documents as lists of words, but then dropping the order of the number of occurrences. We ended up with sets of words. Then we saw that you can interpret documents as vectors of Booleans, and that based on this, you can build a so-called standard inverted index that has a structure on the left that organizes all the terms that you get in a B+3, for example. And then we have, and now we know how it's called, right? The purple rectangles, these are called the document frequencies. And then in the blue rectangles, we have the document ID. So here it's sorted by document ID. This is the standard inverted index. And by now, you know that there's at least 10 or 15 different variations of that index, depending on what you want to do, but it always comes back to this standard structure in the end, variation of that. We saw that the structure to organize the term and look them up efficiently can primarily be made with hash tables if you only want point lookups, single terms, or B+3s if you also want to have ranges of terms, alphabetical ranges. So these are the two main structures. The same in database systems. You also have them in many databases. Then we saw last week that we can start ranking documents instead of just outputting a subset without any order. We can actually score the documents and rank them, and then return the top 10 and then the next 10 and so on. So this is a ranked subset. For this, we saw that we could not use the set of words, but instead the bag of words, meaning that the number of occurrences is important. And in fact, the number of occurrences is the term frequency. This is what's called the term frequency. With the set of words, you wouldn't have any term frequency. That would always be 1, right? And when you have a bag of words and you renormalize things with the Euclidean norm, then you end up with documents as vectors of numbers, positive numbers. So they are just points in the vector space in the first quadrant of the vector space because positive coordinates, right? So this is what you end up with. Then when you query, you just look for the nearest documents and that gives you your score. Then we saw that it's a matter of summing up TF IDFs. Okay, so now that I've repeated that for the 10th time, I'm going to start talking about evaluation. So there are design choices when you build a system. Do you use stop words, for example, or do you not use stop words? Should we exclude numbers, just index words and actually exclude numbers? Or should we consider that the phone numbers should also be important, or street numbers and so on? What is the best value for the champions list, right? When we take the top R term frequencies for the champion lists, what is the value of R we should pick? Is it 10? Is it 100? Is it 1,000? I don't know, right? But we need to figure it out, and we need metrics to decide this. Do we prefer to use stemming or lemmatization? We saw it depends on the language, right? If it's English, if it's German, if the verbs are conjugated or rather do not vary with the person and gender and so on. So this is another design choice. Should you weight the query terms or not weight the query terms, right? How should you pick your smart notation system? Remember these 6 letters that tell you how you have the weights in the vectors. Should you renormalize scores with the Euclidean norm or not, or use a different normalization structure, right? This is again part of the smart menu. Which document weights should you be using? Again, the smart menu. How do you decide? Well, in the end, what do you want to achieve? You want to build a system that returns relevant results to people, precise and relevant, right? You want the system to actually be usable. How do we know that? Well, we need to experiment a little bit and then connect somehow to the real life. How do we do that? We ask people. So in order to ask people, some researchers have set up some collections in order to evaluate systems. And the way that this works is like this. You have a collection of documents, part of your evaluation system, and you have a set of information needs. The information needs are basically what people are looking for, not the queries, because the queries is the consequence of the information need. It's what people actually type. The information need is in the brain. So you have the set of information needs and the collection of documents. And the way you evaluate the system experimentally is that you pick a document, you pick an information need. For example, the document could be the information retrieval book, and the information need could be, I don't know, butterflies in Western Switzerland, right? And then you ask an expert or a person, can be an expert, can also not be an expert, and you ask them, okay, is that document, information retrieval, relevant to the information need of butterflies in Western Switzerland? Probably they will tell you, no, that's not relevant, right? So it's a yes or a no every time. Either the document is not relevant or the document is relevant to the information need. This is for one document, one information need, so a pair of these. And what we need to do is to do it for every document and for every information need, the Cartesian product, right? And for every pair, we ask people for relevance judgments. At least one, maybe even several people, and then we get relevance judgments. If it's a single person, that's 1, 0. If it's multiple people, it can be a number, a ratio of people who find it relevant. Now these numbers are small, right? Here we only have 1,398 documents. We only have 225 information needs. Why? Because that's actually a few decades old. We didn't have computers back then, so it was much more difficult. So they started with something small, right? Something manageable that you can do manually. And then you just need to hire people and ask them for every pair of document and information needs. Okay. And then it improved a little bit. So that was called the Cranfield dataset. Then we had a TREC dataset that had 1,890,000 documents, 450 information needs. So that was an improvement. And so you see, the researchers try to improve and improve and improve and come up with datasets that keep getting better in order to test the systems. This data set is independent on any system. It doesn't matter if you're doing Boolean querying or whatever. It doesn't matter. This is just asking people, is this document relevant or not to this information need? Okay. In some cases, or often, you would even ask domain experts, like people who know about the field of that the documents are about. Right. That's for high quality. Okay. Now, I want to say something that I probably already said, but to make it very clear that this is a query, this is what you type, but the information need can be many things. If you type ETH Zurich, you might be looking for the university right here. You might be looking for the Ethereum community in Zurich, Kansas, in the US. Yes, there's a city called this in Kansas. Or you're looking for the extended trading hours, ETH, on insurance stocks, because that might be the name of a company too, right? So you don't know, actually. If you type the query, this is whatever people type, but you don't know. So this is why what you want to look at in the end is the information need. It's what the person was actually looking for, right? Whatever the query was. And conversely, so this is based on the query. Now, based on the information need, I think it's an example I already gave you, right? But Alice might be probably writing some PhD on the impact of global warming on butterfly ecosystems in the southern part of Uri in these years. And there are many queries that Alice could actually be typing in a system. So just to make clear that query is not information. There is a link, but this is not the same thing. Now that I have said this, I will start my evaluation matrix with precision and recall, which we kind of started in the Boolean week, but then we will continue with more metrics than that. So I'm getting results from the systems. Some of the results might be correct. Some of the results might not be incorrect, right? So why could some not be correct? Because this is a system that's implemented. Boolean querying is deterministic, right? Again, it's because we look at the information need, not the query. If we looked at the query, everything here would be green, right? This would all be correct. But if you look at the information need, even though the query might be evaluated correctly, that might not correspond to what the person was looking for. All right. I was careful to put the green a bit lighter and the red darker so that you can all see that, right? So many coming slides. Okay, so how do we compute the precision, which is our first metric? We look only at the return results, what you get from the system. If you look at these results, some of them will be relevant, some of them will not be relevant, maybe to you as a user, or to these people here that you asked, right? So you know it's relevant or not, also based on this. So you can basically put the results in relevant, not relevant, and then compute the precision by dividing the cardinality of the number of documents that are relevant in the return results divided by the total number of returned documents. What is the precision here for these specific numbers, this specific example? 50%, exactly. It's the true positives divided by the returns one, and that's 50%, 8 divided by 16. Okay. Here the precision is, we've already done that. I think even the same ones a few weeks ago. Here the precision is 100%. Here, 0%, exactly. Okay. And here, everybody, 80%, exactly. 8 divided by 10. Okay, very good. So now that's precision. Now let's move on to recall. We also consider the negatives. So these are the documents that are in the collection, but that the system is not returning, right? You don't have them in the results, but they still exist in the collection. So let's put in there, if in these documents that are not returned, some of them are relevant, some of them are not relevant, right? And again, this is based on the evaluation system that we saw before, right? You basically ask these people right here about it. I'm saying that because if you didn't have this evaluation done before, how would you know if they are relevant or not? If you do not even return them to the user, you cannot know. The user cannot tell you, right? All right, but at least in theory, a document you do not return might still have been relevant. So it's a false negative, or it wasn't relevant and it's a true negative. So what do we like here? We like to have documents in there because these are the relevant documents to return. And we like to have documents in there because they are not relevant and you don't return it. This we don't like, this we don't like. These are the documents you shouldn't have returned, but you did. These are the documents you should have written, but you didn't, right? So in order to get a measure of this, we have the notion of recall, which is the total number of documents that are relevant and that you returned, divided by the total number of relevant documents. That's the ones you would have liked. So here the recall is, everybody, 50%, exactly, true positives divided by total number of relevant. Here it's everybody 100%. Here, oh, I directly wrote it. You see, it's easy, right? I probably inverted the slides here. Probably this one should have come before. Anyway, and here, 67, 66.666. Okay, so 8 divided by 12. Okay, great. So precision and recall, in fact, evaluate false positives and false negatives. Precision is about false positives. Recall is about false negatives. And now come these type 1 and type 2 errors. I never remember what is type 1, type 2, but type 1 is for false positives and type 2 is for false negatives. These are the kind of errors. You see the same in machine learning. You have the same kind of evaluation in machine learning. Okay, and here we have the true positives that are the return relevant documents, the true negatives that are the non-relevant, non-returned documents. So again, I like the green zone, the light green zone, and the yellow zone. I do not like the blue zone and the dark red zone. Okay. Now, do we want precision or do we want recall? Well, ideally, we would both like high precision and high recall, right? This is a system that has high precision. Why? Because I don't have so many false positives, right? So the non-relevant positive part is almost empty. That's actually a precision of 80%, exactly. And here we have high recall, not very precise, but we have high recall because we don't have so many non-relevant documents that we don't return. And here the recall is 88, exactly. It's 8 divided by 9. The way divided, by the way, is that 100 is approximately 99, and 99 is easier to divide by 9. So this is how you know it's 88. Okay, just a bit of mental math. All right. So in the end, it ends up in a compromise because it's very tough to get both high precision and high recall. So as soon, imagine you have a system that is high precision, and then you want to improve your parameters to improve the recall, then you're going to lose on precision, very likely. And you're looking for a compromise, compromise between the two. Very annoying when I can't remember how to pronounce words. I will look it up, compromise. Anyway, so high precision or high recall or somewhere in the middle. Let's add a third one, a third matrix in addition to precision and recall. So precision and recall is about false positive, false negatives based on the of what is returned. Specificity, we look on the right to what's not relevant. And we look at how good our system is at not returning the documents you don't want. How good is it? This is called specificity. It's kind of the opposite of recall, the dual of recall, if you will. So the specificity is the ratio of documents that are not relevant and we got them right, we didn't return them, divided by all of them that are not relevant. So it's the specificity. So here it is, everybody, 50%. True negatives divided by all negatives. Here it is 100%, because all of those we are not supposed to return, we didn't return them, so we did well. And here that's the catastrophe, which is we basically dumped all of these non-relevant documents on the user, and we have a specificity of 0, exactly. And here we have a specificity of 60, right? 6 divided by 10. Okay. So that's specificity. Let's add a fourth one, accuracy. Accuracy is what did we get right and what did we not get right? This is what about. But when I say right, I don't care relevant return, non-relevant not return. This is both right? So I don't distinguish. So in order to compute the accuracy, you look at the true positives and the true negatives, everything you got right, divided by everything, all of the documents. This is the accuracy. So the accuracy here is 50%. We got half of them right and half of them wrong. Here the accuracy is 60, right? No, sorry. 60%. It's 6 divided by 10 or 12 divided. No, sorry, I'm not getting it right. See, I cannot even count. So, okay, let's count. 8, 16 divided by 24, right? 16 divided by 24, that's 4 divided by 6, that's 67%, right? So it's 67%, 2/3, exactly. Okay, now it's an accuracy of 100% because we got everything right. And here we have an accuracy of 0. Is this a bad system? Would you buy this? If I sell you a system that does that, who is buying that system? Why are you buying it? Anybody? Who is buying this? Why are you buying this? Exactly. You can just invert it. So I would pay for that. You just return what's not returned and don't return what is returned. The real bad systems are systems like this that just do a mess. You cannot do anything with that. But this is actually a good system. It's just that probably somebody had made a mistake of swapping the two sides, but it's actually a good system. Okay. Now, if you took a machine learning lecture, somebody probably explained to you that accuracy is not a good way of measuring a system, right? And the reason why it's not a good way of measuring a system is that you can actually cheat or hack it. In order to understand that, you need to understand that even though here for pedagogical purposes, I had small numbers of documents in there and it looks like it's kind of even between the zones, in practice, there are many, many more documents you don't return than documents to return. Maybe you're going to return 10 documents or 20 documents, and there's going to be billions of documents you don't return. So how can I cheat and get super high accuracy? So you would add documents to the system that are not relevant. Something even simpler than that. If you cannot modify the documents, but I give you documents, this is it. I give you the web. How can you implement a search engine that has super high accuracy with very little effort? Maybe we can throw the microphone actually to hear when you speak. So you wanted to answer? Yeah.
So basically we could return very little or nothing.
Exactly, nothing. You just need to return nothing. I can give you a search engine with high accuracy to index the web by returning nothing. Here it is. And the reason why it returns nothing is that everything is in there, and the ratio that you're actually computing, so just like there's many documents that are not returned in practice, there's also many documents that are not relevant. If you look for a specific thing over the internet, the vast majority of the internet is non-relevant to you. So indeed, if you do not return anything, you actually are going to end up in a huge quantity of documents that are not relevant and not returned. So you got them right with little effort just by not returning them. And the ones you get wrong, these are the ones you should have returned, and you didn't. So if you do the division, this is close to 100%, because you're going to have millions in the yellow zone and very few in the blue zone. So you get very good accuracy, except that your system is totally useless because you don't return anything. So this is why accuracy is typically not a good way of evaluating a system. So it's you need to be aware of that, right? So close to 100%. Can we hack recall? How do I get 100% recall? Yes, you still have the microphone.
Well, I just return everything.
You just return everything, exactly. If you return everything, you just get a recall of 100%. By doing that, you also return garbage to the user with everything that wasn't relevant, but you get a recall of 100%, right? So this is why you need to be a bit critical with these things, right? You need to pick the right metrics. And this is why that's not it. Just talking about precision, recall, accuracy, specificity is not actually enough. You still need a bit more work to actually get the metrics right. So you need to kind of merge them. Since I told you it's a compromise between precision and recall, you need to find a way of weighting the two in some score that reflects how you're doing with both. And the first idea could be to take the precision and the recall and divide by 2, right? Just take the arithmetic mean, and that kind of takes into account both the precision and the recall. But it's not a good idea either, because the way that works, precisely because you can easily get 100% of precision or 100% of recall. No, maybe not 100% of precision. That would be a division by 0 thing, but high recall and so on. So this is not good. You should not take the arithmetic mean for doing that. In fact, we take the harmonic mean, right? It's the inverse of the mean of the inverses, the harmonic. You know, right? Arithmetic mean, geometric mean, harmonic mean, you know these, right? Who does? You don't. So the arithmetic mean is when you sum everything and divide by the count. The geometric mean means you multiply everything and then you take the square root or whatever power of square root you need to do it. So it's basically a different way of computing the mean. The harmonic mean is the inverse of the mean of the inverses, right? So arithmetic, geometric, and harmonic. Arithmetic mean is, for example, useful to compute your average at ETH. What is your average grade at the end of your studies? This is an arithmetic mean, maybe with weights with the credits. The geometric mean is very useful in finance. In finance, when you look at returns of interest on accounts and so on, and you want to compute on average how it's doing over multiple years, you need to look at the geometric mean, not the arithmetic mean. The harmonic mean, it's useful, for example, also in electronics, when you put resistors in parallel, right? Maybe you saw that. So all of these means have a meaning. And in that case, we want to use the harmonic mean between precision and recall. This is called the F measure, right? And 0.5 is just because we have a weight of half-half each. So this is the other way. Who did electronics? Who does have notions of electronics, resistors, and so on? To whom does that ring a bell? This is basically an electronics formula. It is basically the resistance you get if you put two resistors in parallel. It's the same one actually as this one. Anyway, you just pick the one you prefer. But if you want to generalize and not do it half-half, then you can add a parameter alpha, and then you can say, okay, I care more about the precision, or I care more about the recall. And you can basically balance in this way. So if you put a weighting of 0, you're going to get just the recall. If you put a weighting of 1, you're just going to get the precision, right? And then you can just fine-tune by picking the value of alpha. So this is the F measure, and it's better than either the precision alone or the recall alone. So it's precision heavy here and recall heavy on the left. Who is following? Right. Who understands everything? Almost everything. Okay, so it means the pace is good, right? Okay, so I'm going to continue at this pace. Okay. So at that point, we only considered metrics for a system that returns a subset of documents. We didn't care about scoring or ranking yet, right? It's like the Boolean querying system, for example. I just look at what documents are or are not in the results without any order. But how does it translate to ranked retrieval, right? How do we do it if we have a system that's actually based on for example, the vector space model, and we want to evaluate it? Well, this I will tell you after the break. So I'll see you at 11:15, and then we'll evaluate ranked retrieval systems.